everybody. In this first video, we're going to start introducing word problems. So word problems are extremely important in mathematics. Sometimes we spend so much time just talking about basic formulas or the general information that we kind of forget that all of this has applications. So this section 1.3 focuses really just on applications. And of course, we'll continue to see more applications through the rest of the course. So word problems tend to be difficult for most people, not just students in math classes, but it's hard, right, to figure out life's problems. So they do take some time and they do take some practice. And they do take a little bit of, just determination to get through them sometimes. So what I have here in the beginning are some general steps that you should take when you have a word problem, particularly if you're getting stuck. So sometimes we come across ones that are maybe a little bit easier and you can kind of jump into, but others can be really challenging. So the first thing you want to do, of course, is to read the problem. And usually you're going to have to read it several times. So you shouldn't expect to read through the problem one time and fully understand it. You probably need to read through it a few times to understand it and have an idea of what they're asking you to do. I like to also underline or rewrite key information. So sometimes I'll underline, or if I find I'm just underlining everything, then maybe I'll just kind of focus on and rewrite the key information. I will draw pictures. So obviously pictures aren't relevant everywhere, but if I have a geometry problem or something like that, I like to draw pictures to go along with it. And basically do whatever you need to do to help you understand what the problem is asking, which is hard. So it takes a little bit of time. This is the hardest part, is the upfront piece. The other thing I like to recommend is I like to physically write out the goal of the problem. And again, this maybe seems silly because you're saying, well, there's a question there already. Do I have to really write the goal? And of course, you don't have to do anything, but I like writing the goal because it just helps me focus in on what I'm really trying to figure out. And then also helps me at the end of the problem, once I've solved it, to remember what the question was I was trying to answer. A lot of times we get through the whole problem and you have an answer, and it said something like x equals 10, and we have no idea what we're even trying to do. So writing that goal, I think, really just helps kind of streamline everything. And will also help you determine your variable, right? What you're looking for, what your unknown is. Also in step one, you want to start labeling. So we're going to define our variable, and it's going to represent one of the unknowns in the problem. And I do recommend that you actually, again, write this out. That's right. And write this out too. Just going to help you stay much more organized. And like I said, at the end of a long problem, have a better idea of what you were solving. If there are multiple unknowns in the problem, so let's say you're trying to solve a geometry problem and you need to find both the length and the width. For our purposes right now, we're only using one variable. So we're going to focus just on x or whatever letter you want to use. But you have to find a way to write all unknowns just using a single variable, because we don't know how to solve equations yet with multiple variables. So you want to stick to just one variable. After you have everything organized and set up, you're going to write the equation. That's step 3. And then the easy part now is going to be the solving part. So the hard part is getting set up here. So then you're going to have to solve your equation. And I do, again, recommend writing your answer in some sort of sentence, or at least a sentence-like form. So make sure there's units and things like that. And then you want to check your solution in the wording of the problem. You can also plug your answer back into the equation to make sure you solved it correctly, but really, because it's a word problem, I can't check your equation. There's no perfect check here. So you want to read back through the question, go back to your goal, and make sure your answer actually makes sense. If it makes sense, then hopefully you're on the right track. And if it doesn't make sense, then you need to start over. So for instance, I'll go back to my geometry problem. If I'm finding length and a width, and I get an answer of a width of -5 feet, that doesn't make sense, right? Width shouldn't be negative. So I'm going to go back and look at my work and see where I made a mistake. So let's try a couple examples. Now, the first two, I just took these pictures directly from your text because there was just so much information to try to copy in. So you do have those in your text. And I do have just a little note here at the bottom that this is example 1 on page 127. All right, so I'm going to read it through with you one time, obviously to save time on the videos, but this is a great opportunity where if you need to pause the video at home after I read it through once, pause it, read it through a few more times, and make sure you fully understand the problem. I've already read the question a few times before starting the video, so I know what to expect already. All right, so the graph and the figure shows the median yearly earnings in the United States by highest educational attainment. So that means based on any degree that you may have earned. It certainly looks like you can make more money with more education. However, workers who make more money pay a higher percentage of income in taxes. So it's wise to consider after-tax earnings when deciding if that higher degree will pay off. Another thing, I think more important than just taxes and getting a higher degree, that seems a little silly to me, honestly, is just thinking about the cost analysis, right? So if it's going to cost you $50,000 to go get a master's degree after you finish your bachelor's degree, then you really need to think about, do you really need this for your job or for your career, right? If you want to expand your career and go to another company or the next level, and you know that you're going to get a significant raise, then in the long run, that's definitely going to pay off. If you plan to stay in the same position, then it may take a really long time to pay off that $50,000 loan, and maybe it's not worth it. And then, of course, if we're not talking financially, there's also personal goals, right? So a personal goal of mine is that I would really like to earn my doctorate degree one day. I have my bachelor's and master's in mathematics, but I don't have my doctorate yet, and that's something that I would like to do. Financially, I don't know that it would benefit me that much, I'm being honest, but it's a personal goal. So that's something that I've been thinking about and weighing those pros and cons for myself, where personally I want to do it, but financially, am I able to, right? Doesn't make sense. So just a lot to think about before I'm just saying that you will or won't get a degree just because of taxes. But let's look at it. So overall, people who have higher degrees on average earn more. Now, of course, that's not always true, right? So there's always exceptions to this. I won't lie, my husband is a union carpenter and he makes a lot more money than I do. And he doesn't have his master's. He has part of a bachelor's, he never finished. So everybody's different, right? So there are exceptions. I won't say that there are not, but overall, typically those who have more advanced degrees make more money in the long run on average. And that's what we're seeing here. So someone with a master's degree in general is earning more than somebody who maybe just finished high school. And you can see in red that we have before tax and after tax. Now, of course, this is a bit of a generalization because your taxes depend on a lot of things without getting too sidetracked, right? It's going to depend on if you have dependents as well, if you're a single earner, or if you have two earners in the home, and so on. So there's a lot more that goes into it than just saying everybody pays the same exact tax rate, right? So it's more complicated than this, but you can see that typically the more money you make, you fall into a higher tax bracket. So you pay a larger percent towards taxes. However, if you still compare the yellow bar, those with master's degrees are still earning more overall, even after taxes. So it says that the median yearly after-tax income of a full-time worker with a bachelor's degree exceeds that of a full-time worker with an associate's degree by $11,000. The median yearly after-tax income of a full-time worker with a master's degree exceeds that of a full-time worker with an associate's degree by $21,000. Combined, 3 full-time workers with each of these degrees earns $149,000 after taxes. Find the median yearly after-tax income of full-time workers with each of these levels of education. All right, there's a lot going on there. So I'm going to go back through a little bit slower this time. Okay. So the median yearly after-tax income of a full-time worker with a bachelor's degree exceeds that of a full-time worker with an associate's degree by $11,000. Okay, so those with a bachelor's degree earn about $11,000 more than those with an associate's degree. The median yearly after-tax income of a full-time worker with a master's degree exceeds that of a full-time worker with an associate's degree by $21,000. So now we're comparing people with masters to people with associates, and there's a $21,000 difference there. Combined, the 3 workers, so combined this all together, earn $49,000 after taxes. And here is our question. So we want to find the median yearly after-tax income of these full-time workers. So our goal here is to find the median income. And they're talking about after tax here. So, oops, income after taxes for workers with an associate's degree, bachelor's degree, and master's degree, right? Because we have one of each category. If you read back through, we're talking about all three of those. So our goal is actually to find three things. We want to know how much does someone with an associate's earn, a bachelor's, and a master's earn. And you can see that those values are not filled in on our chart, right? So we're looking for what is this value, and this value. Now we can get an estimate, right? So I'm going to think associate's degree is going to be a little bit less than 40,000. Bachelor's looks right around 50, and master's looks maybe a little bit less than 60 or right at the 60. It's a little hard to see. So I have estimates, but I want to be a little bit more exact, and I want to use an equation here. Now we need to write our variable. I can't have all three variables. I don't want X, Y, Z. I don't know how to solve that yet. That's a little bit more advanced. So I want to keep it to one variable. And what I recommend doing here is reading back through the problem and seeing if there's one that makes sense. Sometimes you can kind of just pick. But if I read through in this case, I'm going to notice that everything is compared to that associate's degree. So notice that we're comparing bachelor's to associates, and then we're comparing master's also to associates. So everything kind of comes back to the associate's degree. So that's going to be the easiest one to label as X. So our associate's degree is going to be X here. Now you can rewrite this X equals the income for an associate's degree if you want to write out a little bit more, but I kind of already have it broken down. So as long as I label it so that I can understand it later, then that's fine. So associate's is going to be X. Now I have to write the other two unknowns using X somehow. So let's read through again. It says a bachelor's degree exceeds. So exceeds means is more than an associate's degree by 11,000. So what this is saying is that someone with a bachelor's degree earns 11,000 more than an associate's degree. Okay, so our bachelor's degree is 11,000 more than the associate's degree. Now let's translate that to math. 11,000 more than means plus, right? So I'm going to see if I can just fit it in right here. 11,000 plus, and then what is the associate's degree? We don't know. We use X there. So it's 11,000 plus whatever that X value is. And then for our master's degree, we're seeing that it exceeds. So again, it's more than the associate's degree by 21,000. So we're taking 21,000 more than the associates. So I'm taking 21,000 and I'm adding it to whatever the associate's degree is. So this is steps 1 and 2. Reading through that question, like I said, you don't have to do this, but I really recommend writing the goal. I think it just helps to focus the problem. It also will help you to define your variable. So to figure, okay, what's X, what are the other pieces going to be? It just kind of keeps it nice and organized so that once you finish solving, you actually know what everything means again. You don't just have this answer and you're like, I don't know what that is. You have it all set up here. So take the time up front and then the rest will be easier once we're ready to solve. Our next step, now that we have the background, is to actually write an equation. So you need to read back through again, think about, okay, what haven't I used yet? Well, I kind of used this yellow part, I used the orange part, I used the blue part for my question, but I haven't used this green part yet, right? Combined, 3 full-time workers earn 149,000. So that word combined means to put it all together. So if we add their salaries together, we're going to get 149,000. So we're saying that someone with an associate's degree plus somebody with a bachelor's degree plus somebody with a master's degree earns $149,000. Notice that I write a lot in words. So math is not just always numbers. We need to actually understand it. So for me, I'm a writer person. I like to write things down. I love to read. So I write things in words first and then translate it to math. So now that I have the basic idea, I'm going to say, okay, how can I write that in math? Well, associate's degree is X. Bachelor's degree is 11,000 plus X. And master's degree is 21,000 plus X. And all of that's going to equal 149. So if I take my time up front, the rest becomes easier. I already have all that background information done. Now, you don't really need parentheses here. I'm just doing that so you can see, okay, this is bachelor's, this is master's, but really we're just adding. So we're going to get rid of those parentheses. And now I can just go ahead and solve. So actually, let's write it down here again so we can see it a little bit easier. So on the left side of my equation, I'm going to go ahead and combine my terms. I see an X, an X, and an X, so that's 3 X's. And then I'm going to add 11,000 and 21,000. And I'm going to get what? 32,000. All right. So now I'm going to subtract that 32,000 from both sides. And I have 117,000. And I'm going to go ahead and divide by 3. And you can definitely use your calculator here. And what you're going to get is 39,000. Now, I will say that in your book, what they do is they drop the thousands and they just write it as a whole number. So they set up their equation as X plus 11 plus 21 equals 149. And then at the end, they get the answer of just 39. And all they do differently is they just remember that we're talking about thousands here. So they add that 1,000 in at the end. But you can set up how you like. I like it this way better. So our question was to find the median income of each of these workers. So what I do now is I take my answer and I go and I plug it back in up here. I have everything set up. I don't have to think about it. I know my X value. I know what my X values represent. So I'm going to go ahead and plug those in. So our associate's degree is just that 39,000. Our bachelor's degree, we're going to take that 39,000 and we're going to add 11,000 to it. So I have 50,000. And then our master's degree is 21,000 plus that 39,000. And I have 60,000. Perfect. So now I have my 3 values. And of course, let me move it up for you guys. I'm going to save some time here because these videos get kind of long, but you can write this in a nice sentence if you want. But here, I mean, this is pretty well labeled, right? I can see right away, okay, associates earn 39, bachelors earn 50, and our masters earn 60,000 after taxes approximately. And if we go back to our chart, you will see that these numbers actually match up with the line. So they look like they're right in the ballpark. That's kind of a nice quick check here. If I have a graph, I can see that my answers seem reasonable. You can also check it, make sure. So, I mean, everything is positive, which is good, right? If I had a negative, that'd be weird. If I add up 60,000, 50,000, and 39,000, I should get 149,000, which I do. So I have a few different checks here that look good, right? My sum adds up, my graph looks on target. So I feel pretty good about my answers. All right, let's do another kind of similar style example with the graph. And then we'll mix it up. All right. Also, this is example 2 in your text. Again, it's just made notes on page 128. And it was a lot to just try to type in, so I just copied it. It says, researchers have surveyed college freshmen every year since 1969. And it shows that attitudes about some life goals have changed dramatically over the years. In particular, the freshman class of 2018 was more interested in making money than the freshman class of 1969 had been. In 1969, 42% of first-year college students considered being well off financially essential or very important. For the period from 1969 to 2018, this percentage increased by approximately 0.8 each year, so 0.8%. If this trend continues, by which year will all college freshmen consider being well off financially or financially essential or very important? So one thing to know, if we're talking about all college freshmen and we're talking about percentages, all would mean 100%. So they want to know, okay, when is that number going to be not 83, but 100%? So read back through again, underline or rewrite some key notes here. So one thing I'm going to note is that in 1969, my value was 42%, right? And I can see that right here. And then I also know that from 1969 through 2018, this percent increased by about 0.08 each year. So again, that's 0.8, 0.8, not 0.08 percent here. And then next I have my goal. So if this trend continues, so meaning this kind of same change is happening each year, by which year will all freshmen consider being well off financially, essential, or very important? So our goal is to find the year when 100% of freshmen consider being financially well off, essential, or important. So think about it. What am I looking for here? I'm looking for a year, right? That's what I want to find. I'm looking for the year. So I only have one unknown here. I'm just looking for a single year when that value is going to be 100%. So I don't have to worry about having multiple variables or things like that, or how I'm going to rewrite them. I just have one unknown. If I have one unknown, that's my variable. So we're going to let x equal the year when 100% of freshmen, I'm just going to say agree with that statement, just to save some writing. So I'm looking for the year when the value is 100% for these freshmen. Now I need to figure out an equation. So this one does require a little bit of knowledge of those linear solving that we kind of did before and thinking about what's happening here. So I have a starting value, which is that 42%, and I see that it's changing by 0.8% each year. Notice that my units are the same. I'm looking for a year and my trend is each year. So you are going to see some consistency, hopefully, in your problems to make it a little bit easier. So one thing I can do here is think about my equation this way. So I have a starting point. And then what's happening here is I have what is changing by. So I'm having a change per year. And that's going to equal an ending value. And I'm trying to keep this very general so that you can apply it to not just percents or this specific example, but other things that change consistently. So this is a consistent change. And when you have a consistent change, you're actually going to see a nice linear equation. So you're going to see a line here when the change is exactly the same from period to period. So we're going to start with our starting value. And our starting value is 42 here, so 42%. And what is our change? Our change is 0.8. Okay. And we want to get to an ending value of 100. Now I need a variable here, and it comes in right here. When I see change per year, that means it's not just 0.8 one time, it's 0.8 times however many years it's changing. So I'm going to let that x value represent that year here. Now, I'm noticing something as I'm going through, I'm looking, I'm saying, I'm a little bit off here. So I notice my X value is the change per year. And then I have X as the year when 100% of freshmen agree, but those X's don't really match, right? This is per year, how many years have passed, and this is the actual year. So I'm going to make a little tweak here. And this is something we often do with time. So instead of just having X be the actual year, I'm going to have X be the number of years since 1969. And this is a really common thing to do with time in particular. It doesn't happen with every single example, but a lot of examples, if we're looking at that change, instead of starting back at X being like year 0 or year 1, we look at X being the change in time instead. So because we're focusing on a change per year, and we have a starting year of 1969 in this case, is the percent, right, from 1969, then what X is going to be is actually the number of years since 1969. So I'm going to make that tweak. And this is a pretty common thing to do. It just makes the equation much easier to work with, and then also kind of easier to solve because you don't have to worry about being in years before 1969. It's kind of weird to think about X equals year 0, right? That doesn't make sense for college freshmen. So we're going to make this slight change here. So this is a really common thing to watch out for. And now I'm going to go ahead and solve. So I'm going to subtract 42 to both sides. And I have 58. I'm going to divide both sides by 0.8. You can definitely take out your calculator here. And what you get is 72.5. Now, because we're talking about a full year, I am going to round this. So this is about 73 years after 1969, right? So remember, our X value is about the years that have passed since 1969. So to actually answer the question, it's not just 73, right? We're not in the year 73. That doesn't make sense. We're 73 years after the start. So I'm going to take that 1969 and I'm going to add 73 to that. And I get 2042. So we're going to estimate that in about 2042, all freshmen will consider being financially well off essential or very important. So the thing that I want you to take away from this example here is thinking about changes, that kind of linear setup, and then also time. So not every example, but a lot of them, we use this idea of if we have a starting year or a starting month or something like that, instead of just our variable being the year, we do like the years since that starting value or the months since that starting time. And this is a pretty common thing to incorporate. So that's something that I want you to watch out for as you're going through other examples that look similar. This is a little kind of tip or trick that you can remember. Now, one thing I do want to note is we are estimating here, right? So we are making a big assumption that this 0.8 trend is not changing. And 2042 is pretty far away from 2018, right? You're looking at over 20 years. So again, we're going to take this with a grain of salt, right? We're assuming that nothing's going to change in the next 20 years and students are going to be still feeling that same way about increasing financial security. Perhaps something very different happens in 10 years down the line, and this could be different, right? So just something to keep in mind when you're estimating or using your real world data. We don't want to estimate too far out. 20 years is pretty far. So we want to be a little bit careful that that number may not actually be exactly 100 there. But it's still a good idea that we can see the trend right? That being financially stable is becoming more and more important for students.